All right, I'm remaking this video because the first time I did, the sound did not work. So we're talking about lines of symmetry. And so symmetry sometimes is like fold symmetry because you can literally fold it on top. So with this heart, and you can do this with me if you have these type of handouts, but I could fold this over and it would land on itself. That's a line of symmetry. Or I have this, what's called a mirror. There's a beveled edge on one side, thick side on the other. So you put the beveled edge on where you want it to reflect. So you can see here the heart's reflecting outside of the shape. So you keep tilting it till it reflects on itself. That is a line or an axis of symmetry is what we call that. So this would have one fold or one line or one axis of symmetry. Same thing here. You know, if I tilt it, you can see how that goes outside of it, right? So you want to tilt it till it's on it. The other thing you could do is cut these out and fold them. And so right there would be our line of symmetry or axis of symmetry. Now a circle, if I fold this, I could find, I don't know how good, I'm just going to eyeball it. But if I folded it on top of itself, I could find the diameter, but I'm just going to eyeball it because of time. But if you notice, pretend that's the center there, you would have infinite many lines or axis of symmetry because, you know, you can always cut in here more because a circle will always fold on itself. So here there's infinite many lines of symmetry. Sorry about that. Infinite many lines or axis of symmetry. Now there's also what's called rotational symmetry. And so this would also have like basically any degree, like n degree rotational symmetry. Because if I put like a pen here, if I rotate it, you know, 90 degrees, it's going to look the same. You know, 180. If I rotate it just even 1 degree or 2 degrees or 5 degrees, like it's going to look the same. So this also has rotational symmetry and basically any amount. So any n, I could use a variable like 1 degree, 2 degree, 3 degree, anything. Okay, this rectangle is going to have one here. I could fold it here, and I could also have one in the middle here. And again, I'm just eyeballing these. Sometimes students think there would be on the diagonal, and so I cut out a rectangle, right? And you can see if I fold it this way, again, you know, there's one right there, one of my axis of symmetry. If I fold it this way, you can see the other one right there. But notice if I try to fold it on the diagonals, see how it goes outside the shape, okay? It doesn't have any lines of symmetry or axis there. And you can also use the mirror tool for that. If I put it on the diagonal, see how it reflects outside of it. So this one only has 2 lines of symmetry. Now, there is a formula. If I have 2 lines of symmetry, I can take 360 degrees divided by n, and n is my number of folds or number of symmetry to get rotational symmetry. So I have 1, 2 lines of symmetry. So when I divide by 2, I get 180 degree rotational symmetry. And what that means is if I rotate this 90 degrees, you know, it doesn't look the same. But if I rotate it 180, it looks the same. I can't tell the difference. So 360, because there's a circle, you can see that there's 360 degrees in a circle. The 90 degree doesn't get me to where I want. I need both of these together. I need 180 to get it, you know, back to where I'm at. Here we have an equilateral triangle. And again, I could use my mirror and see that there's going to be one there. There's going to be one there. I don't know which ones I all did, but there's going to be one here. And again, I'm eyeballing these. We could measure to be perfect, but I'm just eyeballing. So this guy has 3 lines or axis of symmetry. Okay, so 3 axis or lines of symmetry. So again, rotational symmetry, this should have it as well. So 360 divided by 3, because I have 1, 2, 3 fold symmetry is another word. So if I rotate 120 degrees, I get back to where I'm at. And notice that's these 2 angles together, these 2 together, and these 2 are all 120. If you take, see how there's a circle in them? 360 divided by 3 is 120. So if I take and put my pen in the middle and I rotate, you know, 60, it's not going to look right, right? But if I go a full 120, do you see how I get back to where I started? Or not started, but it looks like how I started. If I go another 120, it looks like how I started. And then if I go back another 120, I get exactly where I started. But rotational symmetry is when you rotate it and it looks the same. This guy has no lines of symmetry. And again, you can see if you go here, it goes outside the shape. I don't know if you guys can see that direction. You can see on the diagonal, maybe if I tilt my paper a little bit and tilt my mirror, it doesn't work there. And I can't remember. I think I showed you that one. Maybe I didn't show you this one. This one doesn't work either. All right, this is isosceles. Just have one trapezoid. Isosceles trapezoid mean these guys are congruent on the side. So it would flip over and have that type of symmetry. And if there's only one line of symmetry, we don't say it has rotational because 360 divided by 1 is a full 360. So that's nothing special. All right, let's look at this guy. All right, so when you look at this right away, you might be like, oh, you could fold it here, right? And it would fold onto itself and here and here. So that's 3. But also notice if I reflect it at these middle points, do you see how, and I can kind of be off. So here I'm actually on, you can see how it reflects on itself. If I tilt it, do you see how when I get to this kind of halfway point, those reflect on themselves as well. So I also have an axis or line of symmetry at these points where they kind of dent in. And so I have 1, 2, 3 through the points, 4, 5, 6 through the halfway point. So I have 6 lines or axis of symmetry. Again, you could call it fold symmetry, any of those. And then again, I'm going to have rotational. So 360, n is the number of folds. So that's what, 60 degrees, okay? So that would be, again, you can see like these 2 angles together, these 2 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 together. Because if I just rotate it there, it doesn't look the same. So if I rotate it this full amount right here, which is 60 degrees, so I'm going to rotate it 60 degrees, see how I get back to looking like I started with. So it's not exactly back where it started. It just looks with that point straight up, and I'm running into stuff. And then eventually you're going to get back to where you started from. So that's rotational symmetry. So that would be 60 degrees rotational symmetry. This triangle is an isosceles triangle, so the sides are equal, and then like these base angles are equal. Again, it's just going to have one fold, one line symmetry. All right, I want you guys to go ahead and do this one. So figure out how many lines of symmetry or axis of symmetry or whatever you want to call it. And then also find the rotational symmetry for this one. All right, I'm going to pause for a second. There's a couple problems I want to look at in the book, and then we'll come back here. Give me a second to open up my book. I'm back, and this is page, 621 in your book. But sometimes you can slide things like wallpaper, and that is symmetry, kind of like translation, like you're sliding it along. Kind of same thing here. We'll talk about this in a little bit. This one also, now this one has rotational symmetry, but not axis of symmetry. So sometimes you can have things that have no lines of symmetry, but it has rotational. So do you guys see if I put this here, do you see how the little curly cues reflect the wrong direction, right? Like it doesn't reflect on itself. And so there is no lines of symmetry, but if I draw in kind of a little bit of a, let's see, where's my other pencil? If I draw in a little pentagon here, kind of on the points of these guys, and kind of make a little, I don't know, spokes or like a circle in the middle, notice that if I rotate it, though, it looks the same. Like if I take my book and I rotate it, it's going to look the same. And so there is rotational symmetry. Now, I don't have any folds, but I need to realize like it's kind of like a 5-pointed thing here. Or if I make a pentagon, do you see how there's 1, 2, 3, 4, 5 angles in the middle? So I'm going to divide by 5. 5 goes in there. 7 times would be what? 35, 10 left over. So 72 degrees rotational symmetry. If I rotate it 72 degrees, it's going to look the same. Okay. So that's another type of symmetry. A frisé pattern is another one. This is a glide reflection. So notice like if I just reflect it across, right, like the little curly Q guys are going to be backwards. I don't know if you can see that. And if I reflect it this way, they're going to reflect, let's see, where's my little point? I don't know. Again, it's hard sometimes to get this, but see how they reflect in the in-between? They don't reflect, you know, line up perfectly. So we call this a glide reflection because what you do is you slide or you glide and then reflect, glide and reflect. So this little curlicue, if I slide it down a little bit and reflect it over, it will line up. So this is a frise pattern, and it's also like a glide reflection. And again, a lot of times you see this stuff in real life, like quilts and art and things like that. You'll see a lot of symmetry. So here's an example of some fabric which has lots of, lots of symmetry in it. So humans like symmetry. All right, so basically just turn in your notes to me and then do the square for lines of symmetry and axis of symmetry. And again, I am so sorry that the sound did not work the first time around. Hopefully it did now.